Morning, everybody. My name is Andy Gregorowicz, and you're here to learn about implementation approaches to FHIR Resource Storage. So just a quick bit about me. I work for the Mitre Corporation. We're a nonprofit that operates federally funded research and development centers for the US government. So you can kind of think of us, some people think of us as a think tank. I like to think of us as a code tank for the US government, but that's some of the role that we play. I've been working in healthcare as a software engineer for about 10 years, and I was a core developer of a FHIR server that's implemented in Go. That's actually, if folks are familiar with synthetic mass, if you've ever played around with that, that is the FHIR server behind that. I also kind of sink down in my seat a little bit because it is on a weird version of FHIR. Sorry about that. And I've also had a lot of experience in the healthcare space coming from the CDA world. Worked on a project called Pop Health Cypress and a relatively popular Ruby library for handling CDA-based standards called Health Data Standards, if you ever need that. So what's the context of this talk? In the work that we do for Mitre, we really wanted an implementation of a generic FHIR server. We wanted to have at our disposal a piece of software that we could use to really perform the full suite of operations that come along with FHIR. So we wanted to be able to have all the CRUD operations available to us for the RESTful interface to FHIR. And we wanted to have the ability to scale our FHIR server. And when we started on this journey, we're talking about 2014, 2015. So think about the DSTU2 timeframe. And when we were having this conversation, you know, the scale that we were thinking about is about 1 million Synthea patients, which back at that time was kind of a big deal. I know there's a Google talk after mine, and they're going to talk about 500 million patients. So I'm sort of the hors d'oeuvre for the entree that you'll have afterwards. But for us, this was kind of a big deal. So you know, we wanted to have a server that we could really throw 1 million patients into, do all of the operations on, including search, and be able to build various kinds of prototypes on top of that. Now, what I will say here is that, you know, we're going to talk about how we store our resources. What you see here may not necessarily apply to you if you're, you know, building something like a read-only implementation or an implementation against a legacy system. You know, really, we here had full control over the data store. So, you know, just keep that in mind as we go forward. So if you're building a generic FHIR server implementation, and what I mean by that is you have a FHIR server that essentially will accept any of the resources that are part of the specification and be able to support all of the operations that the RESTful interface provides. Generally, the controller layer, if you're thinking in an MVC pattern, in a model view controller pattern, is relatively straightforward. If you go through the FHIR specification and you take a look at the RESTful interface, it's about a page of the specification, and you can actually read it front to back. It's pretty understandable, pretty clear. And you can, oftentimes, if you're clever, you can just write a single controller, a single piece of code that'll handle all your web requests that come in and use that to direct things around. Resources, however, this is where all the variation comes into the FHIR specification. You know, there's on the order of 100 resources that are available. And so, you know, oftentimes you want different models to handle these various different resources. And search is different across all of the resources. They have different types of search parameters. And you know, oftentimes you need to interact between these different resources as you are implementing part of the FHIR search API, which is where things start to get a little bit more complex and a little bit more difficult. So FHIR has this notion of something called chained search, where you can ask for you know, patients that have a particular condition. You have things like include when you're doing search, so you can actually pull back other resources, and rev include, which goes in the other direction. So one of the things that we found was resource persistence, being able to, you know, when resources are coming into our server, figuring out how to write them out to disk into some sort of data store was one of the hardest things that we had to do. So I'm going to cover, this is sort of our code Odyssey that we had over the past few years. And so hopefully what you can take away from this talk is there's a bunch of folks here that have actually helped work on this code. So from our collective skin knees, hopefully you can learn some lessons and avoid that for yourself in the future. So what I'm going to talk about is really 4 different approaches, but one very briefly. We're going to start off with relational databases, where we're going to talk about, very briefly, a traditional data model, your third normal form. Then we'll talk about a single resource table. We'll move over to document-oriented databases, which for most people that means MongoDB. It certainly does for us, where we have a resource per collection. And then we'll finish up by going back to relational databases, where we look at a resource per table. So I wanted to quickly talk about, what if you were to take FHIR and try to build what I would consider a traditional data model for this? So, if you grabbed the DBA and said, like, let's put this thing into third normal form. In my opinion, and feel free to disagree with me, this is really impractical. The structure of FHIR really wasn't built with this in mind. There are repeatable elements and complex types that have a tree structure. So this really makes it hard to fit into a relational database, sort of by taking in a FHIR resource, either parsing the JSON and XML, yanking all the data elements out of that, and trying to write that into a database table. So for instance, if you were to look at just something as simple as patient name, which winds up being a human name, you can have the relationship between patient and human name would be many to many. And then human name to given name would also be many to many. So you would wind up having join tables in between those, and that's just on patient name. If you start to look at the codable concept, trying to fit that into a relational database can get kind of hairy pretty quickly. So we sort of threw that right out the window right away. So then another approach to this is to look at a single resource data. So this approach, when you do something like this, you take in a resource and you store the full serialized resource in a single table. So oftentimes databases have support for blobs or clobs, where you can just take that hunk of JSON or XML and just throw it into a column in your database. If you're on some of the more modern relational database platforms, Postgres has support for JSON storage directly, so it can be a little bit smarter about it. But that's typically how things work, where you just throw your resources into a single table. Sometimes you'll have metadata columns that you're extracting, so you'll have your giant resource blob, maybe you've pulled out the ID, and maybe you've pulled out some additional metadata so that you can use that to help support search. And then oftentimes when you're doing that, you're also extracting elements so that you can support search as well, so that you don't have to dig all the way into the JSON or whatever whenever your search requests are coming in. So an example of this, and I chatted with James about this a little bit, is the HAPI FHIR JPA server. So I'm guessing that by this point in the conference, if you haven't heard of HAPI yet, I don't know where you've been. But HAPI is a very popular Java implementation of the FHIR specification. They provide a full stack implementation of FHIR, and they follow this approach where all of their resources go into one table, and then they have some metadata that is split out to support searching. So you can see there's a whole bunch of other tables here that are associated with a particular type. So string types get pulled out into their own table that are used to support searches and things like that. So when we first started out, we pulled down HAPI. We were like, great, there's a FHIR implementation. We'll just go and we'll use this. And there are some nice attributes to this sort of approach. So your schema doesn't really change when there are changes to the resources. That's really nice. So as you're moving from specification versions, or if you're trying to follow it really closely, your database doesn't change very much. Your database access is also uniform. There's one table, and obviously you have all these other search index tables, but it really makes it sort of can allow you to have a uniform controller layer as well as a uniform database layer. So what are the downsides to this? You have an awful lot of joins. And when we first looked at HAPI, and I've talked to James, and I know they've made a ton of performance improvements. We haven't had a chance to kind of kick the tires on it again. But sometimes you can even have a join per search query if depending on how you put this together. So every time somebody's passing in a search parameter, you need to join back in an index table. And that can just wind up being very, very expensive, very difficult on your database over time. I'm guessing people in here are familiar with ORM technologies or object relational mapping technologies. Many programming languages have, or programming frameworks have support for wrapping your database tables and just providing you some convenience functions as opposed to having to write raw SQL. Doing this sort of self-join nature over and over again, depending on your ORM framework, can give you fits. Some of them probably handle this better than others. And when we were trying this circa 2015, what we found is that the performance just wasn't acceptable. Again, we haven't kicked the tires on this recently, but speaking to James, he's saying they've made massive improvements in the performance of HAPI. So please don't take that as sort of a as relevant a statement in 2018. So at that point, we thought, well, we're developers. We love to build things ourselves. So let's give that a whirl. And we were very, at Mitre, we had built a lot of solutions on top of MongoDB, which is a document-oriented database. It stores JSON documents natively. We thought, this is wonderful. Because FHIR is in JSON. We'll ignore XML because we have the freedom to do that. And so we'll just take these FHIR resources, we'll throw them directly into our database, we'll treat them as documents. And what we decided to do is that we threw each resource type into its own collection. So it was great. If you opened up our MongoDB database, you would see there was a patient collection. It was full of patient JSON documents, conditions, observations, all that. They went straight into the database. And so we use that to implement a Go-based FHIR server. So this is our FHIR server. It's based on the Go programming language. It is the FHIR server behind synthetic mass. If anyone has played with that, that is a publicly available website at syntheticmass.mitre.org. It is a 1/7 simulation of the population of the state of Massachusetts, so it contains about 1 million patients. It currently supports JSON only, and again, I apologize, it's on sort of a weird version of FHIR. We handle search through this by plain queries in MongoDB. So if you're just searching on a resource and you're executing it with just the basic search parameters, we can handle this with MongoDB right out of the box, and it's beautiful because if you look at the search paths in the FHIR specification versus the query language in MongoDB, they map together quite nicely. So that was really, really nice. But then for everything else, like chain searches, reverse includes, all that other stuff, we had to drop into the aggregation pipeline, and that's where the headaches started. One other thing, and I heard this a little bit in the Google Protocol Buffers talk, and this is just something to be aware of as developers in FHIR space if you haven't been around the FHIR world for a long time, is that FHIR lets you do all sorts of stuff that maybe as a programmer coming from other realms you might not be super comfortable with. So they allow extensions on primitives. We just threw that out the window and said we weren't going to support that. However, we had to do things like we wanted to use the native date time types within the MongoDB environment. You may want to do that within your database. You have to be aware that FHIR allows arbitrary precision in some of those fields. And so if you're going to deal with that arbitrary precision, if you want to reproduce that back to a client, you need to record the precision that comes in. Also, we did some special handling of references. So when you have FHIR resources that are referencing one another, you can have a reference that might point to a resource locally on the server versus something that points to another FHIR server. So we put some extra stuff in our JSON that said, here's a local reference so that we could go and follow it and query against it. We would not return resources that were handed to us that reference outside of our server. So what happened with our document-oriented database? We were able to make it work for synthetic mass. So we were able to reach our scale of 1 million patients, which was great. As I mentioned, basic search was straightforward. It was really easy to convert the FHIR search expressions into MongoDB queries, so that worked out incredibly well for your simple search cases. However, now moving into the document-oriented database field, we felt the lack of many of the relational database features. And so we had no joins, which made doing things like reverse include, chain searches much, much more difficult. And what happens is that pushes you into the aggregation pipeline in MongoDB. And this isn't really a tutorial on MongoDB, but our observation on that was that essentially you have to create the pipeline for the query. So you're saying, okay, if I'm doing a change search, I'm going to look at all the conditions first, and then I'm going to join that back into the patients, and so on and so forth. What that does is it makes the developer the query planner. which is not the best position to be in, especially if you're looking at other relational databases that have had several tens, if not hundreds of person years put into it. Now you're the query planner, and again, you're doing this at compile time as opposed to at execution time when you don't have all the information available. This also makes paging difficult. So paging was really hard for us because you can't just sort of say offset and jump into it. It has to kind of execute the whole query. And surprisingly, I don't know if this has changed recently, but MongoDB has terrible performance on just counts, and that makes no sense to me. But just even asking for a count size in a collection took a really, really long time. So that's one of the dirty secrets. If you go to syntheticmass.org and look at our bundles, we don't return bundle counts. We actually had to turn it off. Even if you just ask for conditions, it just performance falls through the floor, and I don't really have a great explanation for that. So this brings me to the last sort of experimentation phase that we've been working on, and this is storing things where we have a resource per table. So this was similar to our document-oriented database approach, and what we decided to do is we wanted to find a space where we could get the best of both worlds. And really, what changed for us in the environment was that we started to notice, most notably Postgres, but MySQL has support for JSON as well, where modern relational database platforms have become really, really good at handling JSON. So I saw a slide from one of the Postgres talks where it said, that Postgres is a great relational database and also a better JSON database than MongoDB. And I'm not here to put out those sort of fighting words, but we're kind of finding out that's sort of true. And so we wanted to use those JSON capabilities, extract some of the key elements to support search, and then handle the remaining searches directly through JSON. So we don't have to extract all the elements that into a search index field. You can still just query into the JSON in places where you might need to. So this is an open source project that we're working on right now. It's called Candle, because it's a really small piece of FHIR at the moment. But we're calling it our FHIR microserver. It's written in Ruby because we like Ruby, and we're storing our resources in Postgres. And we're doing that with an approach of having a single database table for each resource type. And playing with this so far is, right now we've been able to make it work at synthetic mass scale. So we were able to push all of our synthetic mass data in there, our million Synthea patients, and it was able to work really, really well. We were able to leverage the plain old relational database features where we needed to support things like chain search. Which was fantastic because joins are really nice. And then we can drop into JSON when we have to. So we didn't extract all the data into different columns. We just pulled out ones that we knew that we were going to need. So for us, we support the US core profile. So we have race and ethnicity on patient. And when you have to query down into extensions, that can be kind of gnarly. So we just pull those into columns and we can just query against them. But for other things like birth date, we just dip down into the JSON. The downside to this, it's currently a handwritten implementation, so we don't have any slick things that look at things like structured def to output all the code like we did with the Go implementation. It's certainly much more proof of concept now than full implementation. You're welcome to go to the repository, hang out with us, but I mean, this is more idea-aware than something that you can go and deploy right now as opposed to the Go FHIR server, which is much, much more robust. And what we found, at least on the Postgres side, is the SQL syntax for querying JSON is non-standard and a little bit awkward at this point, but it gets the job done. So my get off the stage slide here is that what we found is that if you leverage the JSON-specific features of modern relational databases, for us, that looks like the best path forward. If you're implementing your own FHIR resource storage layer, that seems like a great way to go. When we looked at throwing all of our resources into a single relational database table, search to us became really, really difficult. The SQL becomes a little bit more gnarly. Performance started to become an issue. James would be a good person to talk to about this because I know they've been doing a lot of work on this in HAPI FHIR, and they've probably overcome some of that, but that was our experience with it. And MongoDB, what we found when we were really trying to push this past a million, up into a million patient range, that started to fall down on us in the complex query space. So that's what I have. I think I have maybe 30 seconds for questions if anybody has any questions. All right. Thank you very much.
So hi, everybody. I'm Kurt. I'm on the Google Cloud Healthcare and Life Science team. I know many of you saw Eyal's talk, heard Patrick's talk about protobufs. Our team is the underlying infrastructure around a lot of these projects. So when you think cloud, the way I explain it to non-technical folks is I just help rent Google's computers to other people. And then in particular, I make sure those computers can talk to other healthcare computers. And so one of our core products that we've been talking about today, and one of our actually core theses to healthcare, is that FHIR is the way forward. As you can imagine, as Eyal talked about extensively, Google has spent a lot of time in the space around organizing information, making it accessible and useful to humans and machines. The healthcare API in particular implements protocols and formats that are specific to the industry. Again, for the purpose of making it easier to ingest and interact with healthcare data. So I'm often asked, and I mentioned that Google supports FHIR in our API, well, what do you support exactly? And that's a really long answer. This is our conformance statement. This is the smallest font that Google Slides lets me use. It actually goes down about 12 more pages. So it's actually easier for me to talk about what we're still working on, again, because we're relatively new to this community, right? We've been working on this a few years. I know some people have been working on this for 8 years. I in particular, was one of the early implementers of STU1, which, that's a fun story we'll talk about another time. But there are a few things, important features that when I talk about the Google FHIR API that we don't yet support. The two worth calling out of note are subscriptions. There's a lot of use cases around on-demand that we don't yet support. And then a lot of the versioning semantics. These are all things that our team is actively working on. You've probably encountered some Google folks in your visit to this conference. You can ask them about where we are on all these things, but of note, this is what we're still working on. So when you think of a FHIR API, for those who've interacted one before, you are often comfortable with this idea of a base URL. Now, I want to explain a few concepts that are unique to our implementation and those that are common to FHIR in general. So the first bit, the project, this is true of any sort of cloud provider. It doesn't necessarily be us or Amazon or Microsoft. But you set up a project that is your organization. That identifier goes in the project ID, then a location. So this is critical, right? Because the data belongs to you. This is true of all clouds or on-prem. We don't interact with it. It's entirely yours. Yours to set up retention policies. Yours to tell us where you want it to go. So location's the way to do that. Central one is in Iowa. That could also be a group of regions, Europe, to keep the data in the EU, and so on. Data set this is where you get into some unique Google approaches. So again, because we implement multiple modalities, so HL7v2, FHIR, DICOM, a data set is meant to represent a collection of multiple modalities. So you could have HL7v2 data, FHIR data, and DICOM data all in a single data set. The store implements the modality-specific API. So in the case of FHIR, your FHIR store implements STU3, which forms the base URL. Now there's a slight lie in that. There's a wrinkle that we're working out. But conceptually, that's your base URL. So the other thing I want to talk about as a thrust of getting to this story around, this talk's supposed to be about generating lots of data and working with lots of data. Well, I want to take a step back and talk briefly about the infrastructure that sort of underlies what Eyal's been talking about, what Patrick's been talking about, what all the other sort of alphabet portfolios have been discussing with respect to FHIR. So data starts out, a FHIR resource starts out in some arbitrary form outside of the cloud ecosystem. It could be an DB extract or CSV or H7v2 or whatever, just some other form that is not yet FHIR. Its first landing point is some component of cloud that allows it to be ingested. In the case of raw data or binary data, it ends up in cloud storage, which is very similar to S3 if you use Amazon. For HL7v2 and FHIR, again, those are components of the healthcare API. So for HL7v2, there's an MLP Adapter. That's an open source project on GitHub. FHIR implements the FHIR API, which is what we're all here to talk about. The additional step, and this gets to a little bit about what we've been working on extensively and what Eyal has been alluding to, is around how do you then take that data and normalize it into a FHIR store. And we could spend days talking about how that works, but the short version is there's some process that executes against your raw data and puts it in your FHIR store. Now you could stop here, right? This is a common stopping point for a lot of applications. You could say, I just want to serve this as a FHIR API to a Smart on FHIR app. Or I want to serve this FHIR data to my clinics. Or I'm an HIE, and I want to serve this FHIR data to all the providers in my network. Right? This is a perfectly reasonable stopping point when you're deploying the FHIR API, or really any FHIR API. But there's an alternative path, and this is what we've been talking about throughout the conference. And that is to analyze your data in the sort of tools and services that are built on top of cloud, and in particular, the tools and services that are meant to consume FHIR. So on the BigQuery piece, and I think this was a little lost in Eyal's keynote. I don't know if, when Eyal was running those demos on BigQuery, that was really running. There are hundreds of millions of data points, which were running with his network latency in a few hundred milliseconds. That's BigQuery, right? Heavy analysis, stupidly fast. TensorFlow is our machine learning product that we really like. You can configure it. Again, the Brain team is working on open sourcing tools that take the FHIR data and extract it in the format necessary for TensorFlow. But the story does not end there. You could also take the data from BigQuery, so you've done some analysis and oh, this is an interesting feature set. I want to use this as part of my training model. And again, export it ready for TensorFlow. And finally, you then say, okay, well, I want to expose this data to my team so my team can start to analyze it, start to build models. That's what DataLab is for. That's where you develop models, you analyze it, you can visualize data. And when it's ready to deploy it, that's ML Engine, right? That's our hosted TensorFlow engine. And again, it doesn't have to stop there. Why should it? What if your ML Engine predicts a risk score? And what if it wants to create a risk assessment that then feeds back into your FHIR store? FHIR store pub sub says, hey, I got a new risk assessment. Let me down through that back through my ETL to generate an ORU message. That comes back through your MLP adapter and ends up back in your host system as an observation. Right? So the whole chain can work both forwards and backwards. Now, normally this is where I do a really fun demo, but I'm short on time, so I don't want to go do it. Also, I only pretend to be a software engineer, right? And so it's very embarrassing to show my code for me. But if you want to see it not in front of a bunch of people, we can do that on the side. Also, what I'm about to show you, if you're not careful with the budget on your GCP project, can be very, very dangerous. And you'll see why in a second. So again, actually, the Synthea data set is a great starting point. So when I first wanted to say, personally, I want to generate 100 million resources. That's just what I want. I want to do that as a starting point to see if I can, what my throttling looks like. I just took the Synthea data set, again, right off the page. We heard about this throughout the event, but it's phenomenal for testing and playing with FHIR data. Download the 1K, the 1,000 patients, just as a starting point. If you're just looking to get started, it's already bundled and ready to go. And then I have a little Python script, which I realize is hard to read. I did my best to try and fit on the slide, but it sets up basically your store, and it sets up some basic methods that I didn't show here because, again, they're ugly and embarrassing. But the idea is you parse the bundle and you send it to a FHIR API. It doesn't have to be Google Cloud's FHIR API. It could be Vonk, right? You can deploy that on GKE. That's just a container. You could have a HAPI server running on GCE, right? These are all ways to deploy FHIR. It could be any of them. So here's what we're going to do. We're going to take our Python script, our Synthea data, run through Google Cloud, see what happens in the FHIR store. And if you download the 1,000 patients, you run my Python script, what happens? Wah, wah. It doesn't work. And why doesn't it work? The observations in the initial set, you'll notice, contain references to both patients and encounters. These patients and encounters don't yet exist in the store. So what's interesting about our implementation and the spec in general is that it's a little bit ambiguous about how to handle referential integrity, right? This is sort of a critical concept when you're talking about data integrity, but it's also interesting to remember that when you're loading data from an initial source, particularly a bulk load from some other endpoint, how do you want to handle dangling references to point to resources that don't exist? So we made this an option. It's up to you. You can turn it on, turn it off. If you want to turn on referential integrity, great. If you want to turn it off, turn it off. So let's turn off referential integrity and do it again. And what would we get if I ran the script? You would see a little bit of FHIR. Yay, good for us. But why should we stop there? A couple things I want to note on the implementation that we have, we've noticed, again, because our goal is to, in a lot of cases, to take data from multiple sources. So you may have 12 lab systems all sending in raw lab data. And if you allow those lab systems to consume your API through direct puts, you often have identifiers stomping all over each other, right? And this is bad. So one thing we've said is it's sort of up to you to decide how you want to handle that case. Your store can either allow create on update, or it can disallow it. Because again, it's up to you to make that judgment call on how do you want to handle identifiers from multiple systems. The second thing to consider, and this is exactly the point we just heard about a few minutes ago, is how do you want to handle transactions, right? These are notoriously complex, particularly if your underlying database technology doesn't have transactions. So again, our implementations built on Spanner enforces transactions so that if a request comes in, while it has maybe hundreds and hundreds of resources in the bundle, and then independently of that request, another request comes in to update the same resource. Depending on your underlying database, you will either end up in a state where the transaction looks like what you thought it does, or it looks like what you thought it did with a slight mutation. And this depends critically on the extent to which your database itself supports transactions, which is all to say ours does, because we want to make sure that if a transaction in FHIR is executed, that we guarantee that the state matches the state of that transaction. And again, referential integrity and create on update are things you can configure, because it turns out in practice, those are things that people often want to control. So let's do our little experiment one more time. Thank you. Except this time, I'm going to throw my little script in a while loop. So now we have an infinite loop, right? So now we're going to generate 170,000 records over and over again every second or so. In addition to that, I'm going to take it and I'm going to throw it in a Docker container. So those are familiar with Docker, right? You can take an application or a script in my case, and you put it in, you wrap it in a Docker environment, which allows you to then deploy it on Kubernetes. Kubernetes, Google technology, intended to run containers at insane scale. So we're going to do that. So there's some setup code to prepare your Docker container. It's really simple, right? It's just a dumb little script that loops over a bunch of requests. And then we're going to, a handful of commands to throw your container, and this is the fun bit here, to spin up hundreds of them, right? And if I did this right now, what would happen? Fire all over the place. And actually, what happens in practice is you hit your quota limit because you didn't ask me to raise your quota. And we don't want you to do this in general. Also, this would cost, if you do this with thousands, tens of thousands, you quickly get into territory where your budget is a little sad. So I want to end with this one comment, and that is, so why did I get, this talk was, I started with, you want to create a firestorm of data, right? And you want to survive it. How should I survive a firestorm of data? Well, the answer is, you just did. That's it. It's actually simplicity of scale is the whole point. The point of cloud architecture and cloud infrastructure is to make extraordinary scale seem mundane, right? Our FHIR implementation is meant to make it seem mundane, that you can support workloads that are hundreds of millions of requests per day, per hour, per minute. It's all the same to us. There's some contact information for me. Feel free to contact me anytime. Find me at the conference. No, this is not on GitHub yet, because it's embarrassing, but someday, maybe. That's all I got. Thank you so much.